Cheers for that amazing start of the day. It is now my pleasure to introduce the next speaker. Nate Foster, many of you know and saw in the business meeting yesterday, he is the recipient of the Milner Award 2023. I will say a little bit about him, even though he needs no introduction. He did his bachelor at Williams College, he did an MPhil in Cambridge, and then went on doing a PhD with Benjamin Pierce at the University of Pennsylvania. After a postdoc at Princeton with Jen Rexford, he has been a professor at Cornell and a central figure in our department, where I'm now honored to be his colleague and his next-door office neighbor. Today, he is going to tell us about the network is the computer. Nate has done fundamental contributions in programming languages in different areas of programming languages, but he has also done many, many contributions in networking, and he's also a central figure in the CCOM community. So it is my great pleasure to let Nate tell us about the network is the computer.
Thank you for the very kind introduction. What Alexandra didn't say is, if you have her as your next door office mate, your coffee consumption will go way up, because she will go down to the coffee shop and bring you coffee pretty much 2 or 3 times a day. Great. So I want to talk about networks, but this is POPL, so we should talk about some principles as well. If we can advance the slides. We should talk about some principles. So I was reflecting on kind of what are some of the big principles that have guided programming languages over the last 50, 60, 70 years. And I think you can distill it down to a few big ideas. So one is, of course, abstraction. The idea that our field is about finding sort of the right or elegant building blocks for expressing computation. And this is captured well in, I think, Backus's famous Turing Award speech, where he advocated for a shift to functional programming, because not only do they simplify programs, but they allow you to define new abstractions, which is very powerful. Another big principle is modularity. Liskov, of course, spent much of her career working on modularity. So the idea is that we have really big programs. We're not going to make them robust if we have to think about every detail all the time. We want to have ways of breaking down big programs into small programs, of encapsulating complexity, and then reasoning across interfaces. And another principle is precision. One difference that computer science has compared to other disciplines is we can analytically derive exactly the meaning of programs from their text. And work by Hoare and everyone who works on program logics and verification is driven by this insight. So what about networking? Well, networking is also based on many of the same principles. It's maybe not too surprising, because computer science used to be a really small community, and there weren't these kind of strict boundaries between areas like we have today. In fact, I learned this week that one of Phil Wadler's first jobs was writing code for Vint Cerf, who's sort of one of the founders of the internet. So there, abstraction is also very important. And if you go back and read the papers about, say, the internet protocols, when Vint Cerf and Bob Kahn were developing the structure of the internet, they were thinking about abstraction. So they were thinking about how they wanted to find the right building blocks that would let applications be built on top of the network, and also deal with all kinds of variation in things like packet sizing and failures and so on. Modularity is also important. Here I didn't pick a historical paper, but there's a wonderful CACM article by James McCulley, Scott Schenker, and George Varghese that talks about the essential simplicity of the internet's architecture. And they call out modularity as one of the big benefits. And again, the way that these protocols were designed, ideas like layering, have allowed innovation to happen all across networks. So the network infrastructure gets to focus on better support for what the internet does, which is best effort packet delivery. And applications can think about all the rich services that they can build on top of that model. And these things are not really coupled, which allows them to proceed sort of independently. And then there's precision. I called this precision-ish because I think it's fair to say that formal methods and precise reasoning has not been the way that networking has has been driven over most of its history. That's not to say there's none. There are, of course, some great examples of forum methods, even in very early networking. But by and large, network protocols and the internet community have been driven by this slogan. They do have to agree on certain functionality, captured in things like RFCs, but they tend to follow what they call rough consensus in running code. So when they define a protocol, they don't spell out every last detail. They achieve this sort of level of rough consensus, and then they declare success when they can have different implementations that can interoperate. Okay, so there are some similarities between these two communities, but also some differences. And I wanted to just do a little example to kind of illustrate how the network designs and these principles of abstraction, modularity, and precision have played out. So let's imagine that we're building some kind of service, maybe to stream videos over the internet. I don't want to get sued, so let's call it Netflix. And the basic operation of this is going to work, building on the internet. So the beauty of the internet is I don't need to, go talk to every ISP and every cloud provider to build this. I can just stand up a server that has the videos I'm going to sell to customers, and then register a name, and my customers can reach me. Right? So we all know this story. And under the covers, there's, of course, a lot that goes on. So my customers might be accessing their network over a Wi-Fi router, and then they go maybe to some bigger router. On the server side, there's probably some kind of fast wired connection talking over a NIC. And again, the kind of abstractions and modularity that the internet gives, you've probably all seen a picture like this in an undergrad networking class. At the top level, I build this service that maybe provides some streaming video protocol, and my packets kind of go down through the layers, each doing their own job and then flowing back up. So it kind of works beautifully. Or does it? If my service is successful, I'm probably going to get some more customers, maybe a lot more customers. And so pretty soon, just having sort of one box parked at Netflix.com is not going to be enough. I'm going to have to build more boxes, maybe even have data centers, maybe several data centers. And so now I've got this problem that I've got all these customers who want to watch my videos and have them be fast and high quality and so on. And I've got all these servers that are hosting probably replicas of all the videos that I'm serving. And now I need to somehow get the network to steer the customers or their eyeballs to the right servers and vice versa. So what do? Well, first, the most common design would be to introduce an appliance called a load balancer. So this is something that kind of goes against the original elegance of the internet's design, because it's kind of, in many cases, cutting across layers and trying to divide traffic amongst the possibly hundreds or thousands of servers in each data center. I also need to find ways to spread the load coming from my customers, also optimizing for things like congestion and latency. And so I'll use some techniques to do load balancing on their side as well. I might use DNS, sort of a souped-up DNS server to allow customers to direct their browser to Netflix.com, but then have it actually pick the closest IP address of the data center that I want to go to. I might use BGP to, again, help load balance or pick the best paths getting to those data centers. And if I'm really getting serious, I might even have what's called a content delivery network to cache the most popular videos close to the customers, so they actually don't have to even leave their own ISP to get there. Okay, so this is still a cartoon, but somewhat realistic and kind of reflects how these modern web services are built. And if you're me, I don't know, I kind of find this a bit of a horror. It's gotten very complex, and it's not an edge case, right? There's video is very important, and there's lots of services that need something beyond what the internet provides. So, stepping back, I think it's clear that networks have been a huge success, right? Pretty much all modern systems depend on networks in some way. We don't send software around in floppy disks. We use our phones. We power data centers, machine learning. All of these are enabled by networks. But in the SIGCOMM community, there's a growing sense that the internet architecture, and I'll say that the internet architecture and internet protocols have also driven much of the private networks and private protocols that are used just because of the way that network hardware works. And there's a sense that these architectures have kind of gotten ensconced. There's talk of ossification and them being brittle and hard to change. And there's also agreement that some really important considerations were left out of the internet's original design. Back when Cerf and Kahn were designing the internet, they were thinking about problems of internetworking multiple different networks, and they weren't so concerned about things like security, and they also weren't really thinking about extensibility, which today are very important. Okay, so I want to talk about an alternate history. What if we had fused networking and programming languages earlier? So what if networks were just other systems that we could program sort of just like or in similar fashion to computers? Well, so one advantage is network owners, or more generally users of networks, might be able to customize the network to suit their needs. And that might simplify building a service like Netflix, where what we don't want is really point-to-point communication, but we want to somehow deliver content stored on many, many servers to many, many customers. We might also be able to start to use ideas from our community, formal methods, to start to reason about network behavior. And in fact, this vision is not really new. I was reading around and looking back at some history, and actually one of the first articulations of this idea that I was able to find was from a POPL paper from more than 40 years ago, from POPL'22. So David Wall, who was then at Penn State, had this paper on messages as active agents, and he was thinking about how you express network algorithms, sort of basic routing algorithms and so on, and had the observation that you can sort of write these algorithms from two perspectives. You can write it from the perspective of each individual router, or you can write it from the perspective of the packets or messages that are traversing the network. And this was a sort of inspired idea, but I think if we had taken it seriously, we might have ended up in a very different place, which would have some benefits. And more broadly, there has been a long effort spanning multiple decades to try to make networks more extensible and more programmable. I put Wall's paper back in the 80s. There were a bunch of different protocols and approaches that kind of rose in prominence and then fizzled out. So there was a technology called ATM, started in the mid-'80s and kind of rose to prominence in the '90s, that was being pushed by a bunch of telcos and ISPs. There was a major effort funded by DARPA in active networks. I think some people even in this community worked on that. So there, the idea was to really take Wall's vision and make it practical. So to have packets that would carry programs, and you could customize the behavior of routers by sending special packets that would set up certain paths or create different services. And then later in the early 2000s, as things like cloud computing and virtual machines and such became very prominent, the challenges of managing those networks led a bunch of folks to propose what's now called software-defined networking. And they were thinking about new ways of organizing kind of top-down control of private networks. And then what I'll talk about today is, again, about a decade later, there were some folks who thought about designing network hardware that could be customized using a DSL called P4. So you might take a skeptical view and wonder, if people have been proposing, these programmable networks for decades, and I didn't show this, but really, each one has kind of gotten some initial excitement, some hype, and then really fizzled out. What's different this time? And I think there's a couple of things that are really different and mean that these efforts won't fizzle. So one is that there are true kind of pulls from applications needing services and functionality that goes beyond the basic internet model of best effort packet delivery. Some of these are related to network management. So a lot of the early SDN work, for example, was motivated by the challenges of trying to make a big network like in an ISP or a cloud provider. Trying to keep that network working is really hard if you have to express everything in terms of fully distributed protocols. There's also new services. So network virtualization was one of the big drivers of SDN. And there's also certain applications or certain functions that have become very important for reasons of performance or functionality. So traffic engineering, being able to monitor the network to understand what's going on, and increasingly security. So there's things like, if you've heard the buzzword zero trust, at the network layer, this turns into networks that basically set up and tear down forwarding paths based on some kind of policy and authorization. So all of this requires the ability to modify the network at pretty fine timescales. There's also some things that I think are coming from the bottom up. So I call these pushes, architectural pushes. So one is that Moore's law has really ended for CPUs, and a lot of a lot of the ways that people have kind of layered on functionality and services on top of the internet has involved plunking down these special boxes, things like the load balancers or CDNs that I showed in my Netflix example. And until very recently, it's been possible to take a server and get it to process packets at a sort of competitive rate. So you can, for example, get one core to process with lots of tricks about 100 gigs per second of data. But that already requires some heroics, and we're not going to go much further. And meanwhile, the speeds of networks have continued to grow. So 400 gig connections are common now. We're going to 1 terabit, and it's just not going to be possible to do packet processing on CPUs at those rates. There's also, again, these advantages of SDN architecturally of being able to separate concerns, I think is a fundamental idea, and we're not going back for that. And then third, as Moore's law has ended, a lot of hardware designers have started to take devices that were traditionally not very programmable, so things like routers and switches and network cards, and think about how you could build some domain-specific hardware that would still be programmable so that they can host more applications. Okay, so in this talk, what I want to do is, it's not going to be a very kind of programming language talk in the sense that there won't be, denotational semantics or program logics or lots of theorems. But I want to show you some examples of how we can rethink the foundations of networking by taking more of a language-based approach. So we can use networks that are programmable to make them more extensible and to do better reasoning about them, and generally to kind of unblock networks from the current sort of state of ossification that they're in. Okay, so to start, let me tell you a little bit about some of the abstractions that I and many others have been working on for the last 6 or 7 years. And the vision here is really to kind of nudge the community out of its current way of developing new functionality and new protocols. So again, going back to Clark's quote about rough consensus and running code, for many years, the way that if you have some new idea about some new protocol that you want to have supported in a network, the way you do it is, well, first you do some design and prototyping, probably just with yourself, and then you take it to the IETF, right? And you propose a new protocol in an RFC document, and you go through a social process to convince others that it's a good idea, incorporate their ideas, and write it down in some kind of document. So that process takes, sometimes 6 months, sometimes 3 years, sometimes more than 3 years. And then you can then go to vendors and say, okay, I've got an RFC, and look at all these other people who want this functionality, and then you try to convince them to add support for that protocol into their device. And that takes, in the best case, a couple of years, maybe more. And this is not just a story. Like when software-defined networking first became really big, and one of the big uses was network virtualization, VMware wanted to add a new tag, something called VXLAN, to give them sort of more control over how their virtual networks were being implemented. And they experienced about a 5-year delay from having the desire for that feature to having it be supported on, I believe, Cisco routers. So that's just a very slow process. And so what we'd like to be able to do is, instead of having to go through all these rigmarole, to basically just be able to write a program and get that protocol running in a production setting right away. So before I tell you a bit about the P4 language, let me just set some terminology. I won't be talking too much about control planes or sort of the software-defined networking side of things, although it's very important. But I just wanted to sort of set terms and remind you that networks really have sort of algorithms that run at 2 levels. So the one that you probably focus on the most, say in an undergrad class, is the control plane protocols. So these are the protocols that do things like learn the topology of the network, compute shortest paths or spanning trees or other paths through the network. And they're also responsible for managing policy, things like security policies and firewalls and so on. And then the control plane communicates with the data plane, which is the piece of the network that runs the forwarding algorithms. So these algorithms are different. They're really functions on packets, and they are responsible for performing lookups in routing tables, keeping track of usage through things like counters and other accounting mechanisms, and increasingly also doing some limited forms of stateful processing. And I'm going to focus on the data plane here. So at the hardware level, because sort of Moore's law has ended, the way that most data planes are organized is in terms of some kind of pipeline. So this is a different kind of processor than what you probably have inside your laptop or a server. It's really designed for throughput. So the idea is that packets come in, and they go through some number of steps of processing, and then they go out. And so there's no possibility of stalling. You don't really ever visit the pipeline multiple times. And also the program, instead of being a thing that's sort of traversed and fetched like in a binomial model, here the program literally gets loaded into the pipeline. So your program sort of gets sliced up, lowered into the pipeline, and you execute it in one pass as you go through. More generally, the sort of high-level steps of processing that you do in one of these pipelines is first you take bits coming in off of some line card or wire, and you parse those bits into some kind of structured representation. Maybe you're parsing out standard protocols like Ethernet and IP and TCP. And then you do some processing on that typed representation. So you might do lookups in some routing table like I've shown here. You can do other things as well. And then finally, you deparse the structured representation back into bits and apply whatever effect has been computed, so forwarding the packet or dropping it or something else. So the P4 language, which I've been working on for the last 6 or 7 years, is a language that's really a DSL for these kinds of pipelines. And historically, these pipelines were not programmable or not very programmable. They would implement the protocols that are in the internet standards. So different hardware vendors had different ways of doing that, but essentially there'd be some units devoted to IP and some units devoted to access control and some units devoted to other protocols. But P4 was anticipating a class of these routers where instead of having dedicated units for different protocols, you just have a bunch of memories and arithmetic units and hashing units and other things, and you can then program it to implement whatever protocols you like. So in terms of language design, you can think of this as being pretty similar to sort of the data flow paradigm, but of course it has some network-specific features. So first and most important, these pipelines are restricted. So you typically don't have a memory, or any memory you have is a finite size and very small. So you're not going to support operations like malloc or things that can't fit into some statically allocated memory. And also, although it's possible, of course, to visit the pipeline many times with a single packet, it's easy to see that that will greatly hurt your throughput, right? So if every packet's visiting twice, then your throughput gets cut in half, and if it's 3 times, 1/3, and so on. So generally speaking, visiting the pipeline many times is not something that's done. And so if you want to think about a programming model for those devices, it probably makes sense for that language to be restricted in some way so that you can't accidentally write a loop or something that would kill performance. The other features of this language are, the bread and butter of packet processing is manipulating low-level bits, and not just things like, not the sort of normal types of things you use in a language like C, but some protocols have 1-bit fields. So the language has a bunch of types and other features, a rich collection of numerics, a bunch of operations that make that kind of low-level bit wrangling more convenient. And then the third thing is, the data plane is one piece of the puzzle. There's also a control plane. And so there's an important interface between the data plane and the control plane. Namely, the control plane needs to be able to reconfigure the data plane by changing the entries in routing tables or access control lists and so on. And if you're making this programmable, you need some way to decide what that interface is going to be. So P4 has a piece of the language that's devoted to explaining how the control plane can reconfigure the behavior of the data plane. I'm not going to take you through the language kind of piece by piece because really, if you understand those 3 kind of high-level ideas, there's not much more to it. It's an imperative language. It's got low-level bit wrangling stuff. It's got some elements that are control plane programmable, and that's it. But to give you a sense of what programs tend to look like, this is kind of this is sort of a hello world example from 50,000 feet. On the left, you see that most programs actually start with some description of what we call the architecture. And that's because P4 is really a family of languages. We use P4 for programming network cards. We use it for programming routers. And each of those does their work in a different way. And so what the architecture does is it lets us factor out the differences between different kinds of hardware, giving just the shape of the pipeline and if the device allows some other operation, has some built-in functionality, we can expose those in the architecture and use them. So that's what's here on the left. And then on the right is the program that we write. And basically, there's going to be one chunk of code for each of the sort of holes in the architecture. So most architectures have sort of a number of P4 programmable blocks, and the code you're writing is ultimately determining what code goes in those blocks. And so a typical program would have a whole bunch of type definitions, because P4 doesn't bake in any of the standard protocols. You have to define them yourselves. And then we'd write parsers for those types. And again, these could be standard parsers or they could be custom parsers. And then you write what P4 calls controls for control flow, where you explain how to sort of string together different processing blocks together to get the end-to-end program. So very quickly, just tell you about the impact of P4. Again, it's been around, actually, the language has been around for about 10 years. So Dave Walker and Jen Rexford and Nick McEwen and a bunch of other people proposed a first version around 2013 or 2014. And then there was a second version done about 3 or 4 years later called P4.16. And it's had quite a bit of impact in industry. So there's, by now, P4 support on most of the different classes of network devices that you could imagine. So switches, some devices that are called smart NICs. So these are network interface cards that are programmable and have some processing engines on them as well. Just in the last 2 years, there's been support added to the Linux kernel. So you can write P4 code and have it run in the kernel. There's support for doing processing relatively efficiently in user space in a framework called DPDK. And kind of closest to my heart, there's also a growing community, including folks at Google and Microsoft, who are using P4 not so much for programming the behavior of devices, but actually as a specification language. So they're using it to drive testing and validation, and also just to kind of move their specifications of different APIs and functionality into a mechanizable, precise form. In terms of the research community, P4 has become, I think it's fair to say, the way that the SIGCOMM community expresses innovative ideas. Certainly, if it has to do with sort of protocol design or packet processing systems. I did a count last year. I haven't done it for this year, but last year, fully 30% of the papers at POPL'24 used P4 in some central way. So I discounted papers that just cited P4, but these were papers that were using P4 as a modeling language or a programming language for developing their system, which is a pretty big fraction. And then sort of at the intellectual level, you might wonder, well, what are people doing with this language? And there's a growing collection of what you might call in-network processing or in-network services. And some of these are kind of wild ideas that will probably never see the light of day. But some of them, I think, are fundamental. So people are thinking about networks that can do caching or data replication, and where that logic is expressed in P4. There's also folks building different distributed services, so a consensus protocol or a distributed locking service that can be made faster or have sort of different characteristics if you realize it in the network. There's been some work on accelerating things like database transactions using support from the network. There's some work on runtime verification, so building networks that can check their behavior against a specification. And a lot of work on kind of core topics like congestion control. So historically, congestion control works by, when a packet is dropped, the senders will adjust their sending rates and such to avoid congestion. But you can also, of course, use the network to explicitly keep track of when congestion is about to occur or has occurred. And people have used P4 for that kind of monitoring as well. OK, so let me jump down back into an example. This isn't exactly the Netflix example, but it's maybe a little bit inspired by that. Just to kind of think about how we might use a programmable network, in particular a programmable data plane, to implement some new abstraction, let's try a totally different forwarding abstraction than what the internet provides. And that is, we'll allow the receivers to subscribe to a stream of sort of published data. So on the left here, you have the data publisher. So they're going to publish a stream with some format. And on the right, you have the consumers. And of course, if all we're doing is sending the same data to everyone, this is not so interesting. But now suppose that there's either multiple streams being composed together, or the receivers only wish to receive certain kinds of data. How can we build a network that provides that service? And to make it really concrete, this is the kind of thing that happens in the finance industry all the time. The exchanges publish a feed containing the orders that are going through the exchange. And they have a protocol called mold that they use for doing that. It sort of puts together information about multiple symbols into a single message. And then the hosts that are potentially doing things like trying to get a view of what the exchange is, what the market has, or maybe implementing certain trading strategies, they may be interested only in a subset of the data coming from the exchange. So what we'd like is for these hosts to be able to sort of register queries, much like in a pub-sub kind of system, and the network will deliver to them just the messages that satisfy those queries. So if my host is only interested in Microsoft and their stock price, I'm not going to have to get and filter and discard any packets that have to do with other symbols. So to do this, we're basically going to take this abstraction and realize it in an in-network computing system. This is kind of the architecture of the system. So on the left, the publisher is going to have to tell us about sort of what the types of the data in the streams are. We call this the header specification. And then the subscribers are going to repeatedly tell us what queries they want, what packets they want to get from that stream. And we're going to put this into a compiler. It's going to sort of chop these subscriptions up relative to the header specifications, and then push it down into the network in order to deliver, again, just the messages that the subscribers want. I'm not going to talk about this today, but there's a whole interesting question about how you design the network topology and things like broadcast trees to minimize congestion. That's in the journal version of this paper, but I'm not going to cover that today. So if you're interested in that part, it's indeed very interesting and fun, but out of scope for this talk. So let me focus on the language that we use to describe subscriptions. This is nothing deep here. It's really just sort of predicates. So the subscribers can express predicates that are evaluated over the stream of messages. And it includes the obvious things. You can look at the values of certain header fields in the stream. You can compare it to constants. There's one thing that's a little bit interesting, which is we allow you to also express queries in terms of aggregates. So you can, for example, ask about the average value of maybe a bunch of historical terms, and that aggregate will be maintained by the network switches, and then you can use the current value at each moment in time to compare against the element of the stream. So it's a little bit more than just sort of naively predicates on packets, but not much more. Okay, so how are we going to realize this in a programmable data plane? Well, ultimately what we need to do is we're going to assume that sort of every switch receives anything in the stream that's relevant to the downstream subscribers, and then we want to filter the outgoing stream so that it just has the data that's going to the subscribers, and furthermore, we want to send the output streams going out each port on the switch to the right host. So the way we do this, building on some work from actually an ICFP paper that my group did for compiling SDN policies, is to use a kind of decision tree like binary decision diagrams, but with forwarding decisions that leaves. We call these FDDs. And so we can take a set of queries, one for each subscriber, and turn this into a tree. So in this tree, you see there's predicates corresponding to sort of atomic tests we can do on individual packets. And then at the leaves, we have sets of output ports corresponding to the subscribers that should receive that. And once we have this kind of tree, we can chop it up. So we do this for reasons of efficiency, to be able to turn the evaluation of this predicate into a pipeline. And then we decorate the tree with some additional values to keep track of where we are. And then we can basically evaluate this predicate in a pipeline of tables where each table checks sort of just one match condition. So in this example, just checking the price or just checking the shares. Okay, so pretty simple. And if you saw earlier work in ICFP or POPL on sort of SDN programming, it's not that dissimilar. The difference is here we get to define the formats of the packets and of these tables, and we can use that to build this service. So does this actually work? Here's a couple of graphs just to show you the benefits from an empirical network perspective. So this first graph just is sort of a baseline showing you the sort of obvious way to build this kind of system would be you broadcast the stream to everyone and then let the hosts filter whatever they want. And for this experiment, we used a kind of reasonable proxy for the selectivity of the filter that you'd want. I think it was keeping some fairly low percentage of the packets. And there's two plots here showing, or two lines here showing two different packet rates. So the red line is 1 million packets per second, which sounds a lot, but it's not that much. And the green line is 8.25 million packets per second. And this is a CDF of latency. So the closer you are to the upper left, the better. So the red line is basically reasonably smooth and low latency for all the packets. But what you see is that when the data rate goes high enough, because the CPU can't keep up, we start to get queuing and congestion and things slow down. And so here, the latency, especially the so-called tail latency, there are some packets that experience 250 milliseconds of microseconds of delay, which is bad. So here's another graph that shows the same kind of plot. Sorry, the colors mean different things now. But the red, again, is the baseline. So that's that naive, what you would build today with just the internet protocols. Broadcast things everywhere and then filter at the edge. And you see, again, that the tail latency is not so good. And the green is what you get if you can offload some of this filtering work to the switches. And so, in particular, the worst case, it's not perfect. So there's still some filtering that has to be done on the hosts because the switches can't always exactly filter what's needed due to resource constraints and so on. But still, the bulk of the work is being done on the switches, and so we get a much better latency curve. OK, so that's just a taste of kind of what you could do, the new kinds of services you could imagine if you had abstractions that let you customize the network to have more than just basic best effort packet delivery. So next I want to turn to how are we going to build these programs? How do we do this from a PL perspective? And whatever you think of this P4 DSL, it has the property that it's tightly coupled to architectures. So when you write a P4 program, you program the whole shebang. You have to program the entire pipeline. And there's really no support for having multiple programs running side by side. And in code, what this looks like is a typical P4 program, if it's trying to do something reasonably complex, ends up sort of mixing and matching functionality from what intellectually are sort of different pieces. So this is a snippet from a program called switch.p4. This is meant to kind of capture modern data center switch and all the functions it would provide. It has about 45 different protocols. And what you see is this is just one table that does layer 3 rewriting. And what you see is there's a whole bunch of code snippets that have to do with IPv4 processing versus IPv6 processing versus MPLS processing. And they're all mixed together. I've colored them here, but in practice, they're just enabled or disabled by preprocessor flags. And it's kind of a mess. So another thing you can imagine doing is trying to design some abstractions that maybe would still have the essence of P4. So they'd still be a low-level data flow-ish language with bit manipulation and control flow APIs and restricted computation, but try to allow ourselves to write these complicated programs in a more modular way. So in a paper at SIGCOMM a couple years ago, we proposed what we called micro P4. And the idea was really just to do what I said. So we wanted to have the ability to compose these pipelines. And to do that, we had to decouple the pipelines from the hardware. So we proposed this idea of sort of a logical pipeline, which has an input buffer, an output buffer, and then a very simple 3-stage parse, process, deparse pipeline or mini pipeline in the middle. And the reason for this design, of course, is that, and sorry, my lines are not displaying quite like I expected. There's supposed to be an arrow going from that output buffer to the input buffer, but it's very light, so you can't see it. But essentially, you can take these pipelines and string them together in sequence or in parallel with conditionals. This also works if you have things like multicast or packet cloning going on. And basically what you can do is you can build these assemblies of smaller pipelines and therefore decompose and encapsulate the processing for individual protocols into separate programs. Oh, sorry, it's my animation, not the slide. Sorry about that. OK, so the key challenge, of course, is this abstraction makes sense. I think it's probably what many of you would have thought of if you were presented with this problem. The hard part is, how do we actually compile these things? And so the micro P4 compiler, what it does is, essentially it converts all of the different small pipelines, the mini pipelines, into a homogeneous representation. And it does this because all of the targets that are available today, they can only do parsing typically at the beginning of the pipeline. So it won't be possible to kind of do some processing and then go back and parse again. And so the strategy we used for implementing these ensemble programs was do all of the parsing at the beginning. So we need to parse deep enough into the packet to grab any of the data that we might need for one of these pipelines. But instead of populating any specific data structure, we keep it in a kind of generic, sequence of bytes. And then when we do parsing in the individual pipelines, we turn those into just ordinary P4 controls that implement parsing by copying data into different headers and other data types. So in pictures, an individual pipeline might express parsing in terms of this kind of state machine. That's how P4 expresses parsing. And we're going to turn this into a sequence of these lookup tables where in each phase, we're going to capture both the control flow of the state machine and also its effects. So moving data in and out of data structures and then transitioning to the next state. So it sounds a little crazy if you're a hardware person, but does it work? So here's one of the evaluations that we did. We took as a challenge writing a modular router. So a router with support for these, I think there's 8 or 9 different protocols. And then we kind of assembled them into different specialized routers. So for example, this router supports just IPv6, P1, whereas this router supports IPv4 and IPv6. And we compiled these programs. We ran them on 2 different targets, one a software simulator and one an honest-to-God hardware switch. And then we looked at how much does this cost? So our compiler is not perfect, of course. There is some overhead to doing things this way. But if you look at the critical resource, which is how many hardware stages are required to implement these programs, and do we exceed the maximum number of stages that are available on today's routers? The answer was no. So we were there is some increase. In some cases, it's a significant increase, 2x or even a little bit more. But you can fit these programs into again a modern hardware switch. So I think this is again a kind of simple idea, but it shows you what becomes possible if you take ideas from programming languages, make the lowest layers of the data plane programmable, and then start to think about building other abstractions on top. Okay, so in the third part of the talk, I want to talk now about reasoning, or precision. And there's this vision that I think a lot of people have. I even heard it in one of the workshops before POPL, that really with all the technology we have in formal methods today, we should get away from RFCs that mostly have ASCII art and English prose, and we should have these executable specifications of protocols that we can use to verify and to drive validation of implementations. In fact, this is starting to happen. So this is a slide from my former PhD student, Stefan Smolka's Switch V talk at SIGCOMM. So Stefan now leads a team at Google that's doing validation of their data center switches. And their switches are not programmable. So they're not using Intel Tofino switches. And if you look at the total software that runs on a switch, it's pretty huge. So there's the chip at the bottom, there's a version of Linux, there's a bunch of other layers that implement different control plane APIs. It's pretty big. But if you look at what it actually does, it's pretty simple, right? Google doesn't need all 45 protocols that a stock switch from Cisco would give you. They only use a small handful. And they're doing SDN, so their control plane API is also pretty simple. And so Stefan's insight was, we could model this complex on the left as just a maybe 1,000-line P4 program. And it would actually capture both the data plane behavior of these, some small number of protocols, as well as the control plane behavior. And we could use this to drive testing. So this is one of the uses of P4 has been as sort of a precise, mechanizable spec language for either devices, or you could also imagine doing this with protocols. So what I want to talk about is, what would be some of the things you could do that are maybe new and domain specific if you want to do this kind of reasoning about P4 programs. And I'm a little short on time, so I'm going to focus on just one aspect of a P4 program, which is sort of the hairiest aspect, which is how do you parse packets? And as an example, I'm going to take a parser for a stripped down, this is not like industrial code or anything. This is just a sort of a cartoon example to show the ideas, where we're parsing something called MPLS, which is a kind of tunneling header that's used by ISPs. And then there's also a UDP header that can follow. So the point of this parser, expressed here as a kind of state machine, is we can parse some number of these MPLS records from the packet, and then we can parse the UDP header, which follows. And the way this works is MPLS uses a flag in the 23rd bit of each record to say when it's done. So right here, the fact that there's a 1 in the binary representation right here means this was the last record. And then it proceeds to the second state where UDP is parsed. Okay, so pretty simple example. Now, one of the things that happens if you want to run this kind of parser, say on a programmable switch, is the parser is one of the key resources that you need to write your program in a way so that it can kind of parse enough data out of the packet, or you won't be able to keep up with the line rate of the switch. If you write a parser that parses a bit at a time, it's going to be too slow. So what the compiler does is it basically tries to sort of vectorize your code. So it tries to unroll loops. It tries to make each step of processing be wider so that it can fully utilize the amount of bandwidth that's available on that parser. So this kind of unrolling is the kind of thing that the compiler, in fact, does. And so here, if you read carefully, what's going on is, on the right, the first state is actually extracting 2 MPLS records at a time. And so it's grabbing data from the wire twice as fast. Now, in the case where we have an even number of MPLS records, that's fine, right? If we just parse 2 at a time, when we're done, we go parse the UDP and then succeed. But there's this other case, of course, where we had an odd number of records, and so we parsed the last MPLS record and then realized that we'd parsed sort of some of the UDP header already, but we did it in this first state. And so the new variable here, the second record that we parsed, actually contains UDP data. And so we have to add this state here to basically fix up that mistake. We can recover from that mistake. We parse the rest of the UDP header, and then we concatenate the header that we thought was MPLS, but is actually UDP together, and we end up in the same state. Okay, so these two programs can be considered equivalent, and the goal of this work that we did at PLDI a couple years ago was to do that. And the way that we did this was to actually define a language, we call it P4A, which is not literally P4's syntax for writing down packet parsers, but it's very close. And we're going to interpret it as just an ordinary kind of regular automaton. In the interest of time, I won't read through this, but this is just a notation for expressing these state machines where you can do effectual operations in some of the states, like extracting bits out of the packet. And so the first thing we have to do if we want to reason about these is we have to give them a semantics. And so we do that by essentially interpreting these as a kind of standard automaton. So here, the configuration of these automata is going to have the state we're in, the data that we've parsed so far. So there's a finite store, which corresponds to the header types that we parse in the P4 program. And then for administrative reasons, there's also going to be a buffer, which contains all the bits that we may have read so far, but we're not quite ready to execute one of these operations that actually extracts into some header field. And the final configurations here are going to be the ones where, as usual, the state is accept. And we'll then define transition structure over these configurations pretty much in the obvious way. So if we're in the accept or the reject state, then we'll define the transition function to reject if we try to read any more input. This is sort of just a convention that keeps things clean. Generally, you stop when you're in the accept state and don't go further. And then if we're not in a accept or reject state, then we have to define 2 different kinds of transitions. So first, there's buffering transitions, where we read one more bit, and then we add that to the buffer, but we stay in the current state. And we do that whenever we don't have enough bits yet to execute the effectual operation associated with that state, like extracting. Second, if we do have enough bits, so if after reading one more bit we have enough to actually take the effect in the state, then we do the operation, which might update the store, we transition to a new state, and then we empty the buffer. Okay, so this may not be the only way you could do things, but it's sort of one way to realize the mechanics of these P4 parsers, which can sort of do arbitrary bit parsing in a clean finite state model. So we'd like to be able to verify these things. And there's, of course, many techniques we could use, but we're going to use bisimulation. So we're going to prove the equivalence of two parsers. One could be the reference parser from an RFC. Another could be the one we've written in a program. Or one could be the program that we've written, and the other could be the output of a compiler, which is supposed to be equivalent. And so to do this, we're going to use the standard notion of bisimulation. Recall that a bisimulation is just a relation on the pairs of configurations that's closed under taking steps, and it only relates final configs to other final configs. So we'll never relate an accept and a reject state. And in fact, we can generalize this a little bit to capture facts about effects as well. For the rest of this talk, to keep things simple, I'm just going to focus on sort of language acceptance. So we're just going to look at, do the two automata reach accept in the same, on the same inputs. But again, you can extend this to do relational verification and reasoning about the effects as well. There's many ways to build a bisimulation. The one that we use in our tool is to basically build bisimulations from above, by which I mean we start by taking all of the bad pairs of configurations. So these are configurations that are final in one machine but not final in the other, indicated here by these skulls. And then we search backwards, finding any pairs of configurations or any states, if you like, that can reach these bad pairs until we're done. And the complement then is the biggest bisimulation. And so if our start configuration is in that complement, then we're happy because, in fact, the two things are equivalent. Now, unfortunately, this doesn't work because the state space is huge, right? As usual, if you just do this naively with concrete structures, you're going to end up stepping through and searching a very, very large space. For our MPLS example, there's 2 to the 128 pairs of possible configs. So we need a better idea. And the one that we used in this work was based on 2 key ingredients. The first is following the work of folks like Laura Stantoni and others to move to symbolic representations of automata and to compute these bisimulations symbolically. So rather than representing explicit pairs of states, we'll use predicates to capture sets of states. And instead of just following transitions in our automata, we're going to do something like computing the weakest precondition of the predicate that we have at each point through this algorithm, through the procedure that each state represents. So you can view this as, instead of working with points, now we can draw these bigger circles and kind of chase backwards into the end as before. So this is pretty good and helps a lot. But there's one more thing, which is, if you recall the way that we were sort of modeling these parsers, we did it by sort of working a bit at a time to fill up a buffer. And then, when the buffer has enough stuff, we take the step and actually move to another state. And so if you were to apply this symbolic weakest precondition approach to these parsers, what you get is you start with a predicate maybe that represents accepting and having nothing left. And then you go backwards to the states that are reachable from that. And then you'd have many, many, many of these sort of buffering steps, each staying in the same state of the state machine, but the configuration is subtly changing. And we'd have to track that in our weakest precondition calculation. And then finally, we would end up with the place where the buffers have enough and we can take the next step. And so it turns out that you can abstract this, you can sort of simplify this and not actually keep track of these individual buffering steps, because at the state machine level, they look very much like this, right? You're sort of taking a step until you fill up the buffer, and then you do something interesting. And so using the idea of up-to techniques from Bonnke and Poos and many others, you can define an up-to technique for these kinds of automata that lets you basically leap over all these administrative states and just get to where the action is, where you actually do something. So we implemented this. We actually wanted to do this in Coq. So we have a library that encodes P4 automata, their syntax and semantics in Coq. And we also built a push-button tactic that calls out to an SMT solver to check the validity of various first-order assertions about these predicates that we have. So the SMT reasoning is not, we don't get any kind of proof certificate for those, but the rest of the proof that either we have a bisimulation or we don't is verified in Coq. And we also verified the soundness of all the intermediate steps that we do as we take our surface language and massage it into the input for the SMT solver. I think I'll skip over, in the interest of time, a little demo, but you can, well, yeah, I'll skip over the little demo, but it runs and it really is push button. So you just ask it to prove the equivalence and you get back a proof term. Here's one of the examples that we did to verify this. So we took a collection of data center parsers from ANCS paper by Gibb, and we took their compiler. So they have a compiler that takes these state machines and turns them into hardware pipelines. They look like this. And then we built a little back translator that takes the pipelines and re-embeds them as state machines. This is, a translation that we have to trust for the purposes of the final result, but it's a very simple translation that basically just turns this kind of table pipeline back into a state machine. And then we checked if the programmer-written state machine and the one gotten from the compiler with this back translation are equivalent. And we're able to do this for several realistic data center parsers. Okay, so I wanted to step back and just kind of reflect on, there's probably been a whirlwind of sort of different topics and thinking about how, programming languages and networks can go together. I'm someone who, in my career, has not stayed put. I guess, following in the footsteps of some of my advisors, people like Benjamin Pierce and Mike Gordon and others, I've been very curious about thinking how programming language ideas could be relevant in new areas. And I don't know what you do, but when I teach programming language to undergrads, I tell them, even if you have no interest in lambda calculus or semantics or things like this, you're going to go off and do systems or machine learning or computer vision, you're going to find that there's little programming languages problems everywhere. And I think this is actually true. The ideas that our community works on are really fundamental. And thinking about these things not just as kind of, informal, hand-wavy principles, but actually backing it up with, precise mathematical structures and theorems, that's what's so magical about programming languages. And finding ways where you can take these ideas and really, import them or adapt them to new areas is really powerful. Sometimes I feel like I've gone over to the dark side. I've sometimes given talks and people introduce me as, this is Nate, he used to do programming languages, but now he does networking. And I'm not insulted by that. And it is, it's truly a big leap. To really go deep and to understand the problems and methods of another field is a pretty large investment. I've found it extremely valuable, right? You can find new problems, and these are problems that have definitions coming from practitioners or other application domains. And sometimes even if their solution is something very simple, compositionality or bisimulations, solving those problems and really finding solutions that really work often leads you to develop some new twist, which can then feed back and give you some new ideas for programming languages. So at least in my work, I've always sought not to just kind of shallowly apply programming languages to some problems in networking, but to keep my eyes open and to look out for where some new method might apply that might be of interest to our community. And the last thing I wanted to say was, there's this kind of common belief that language design is hard, or at least publishing language design papers is hard. And we all know why that is, right? When you're doing a language design, first of all, you have to do the whole shebang, right? You have to figure out the problem area, you have to define the motivation, you have to design the thing, you've got to evaluate it, and there's no benchmarks or programs out there. So you're really kind of out there on your own. And doing this all in one paper, it's hard to fit it all in, it's hard for the reviewers to appreciate it, and so, I think people shy away from it. But I think, what's really special about our community is everything I said. We're precise, we're mathematically rigorous, and so on. But I think, exporting linguistic thinking to other areas or doing designs is the thing that's most adventurous in my mind and most magical. So I wish our community would do more of that, and I encourage us all to think about ways that we can adjust our publication norms and such so that we can incentivize people to do more language design. I'm really short on time, so I'll just say a quick few words about what's next. There's still a lot going on. So there's a lot of interest right now in the network edge, sort of shifting from the fabric itself to things like NICs and edge devices. There's also a lot of interest in performance. So as network verification has matured, sort of the low-hanging fruit was checking that your routers had the right forwarding tables. But now people want to have guarantees about things like performance properties, isolation, latency, bandwidth. And that requires quantitative reasoning, which is, of course, a huge grand challenge for verification. So I expect to see some exciting things in the next 5, 10 years coming out of the combination of networking and performance verification. And then third, something I'm especially interested in right now is getting back to this problem of the internet. So everything I've told you today really assumes that you don't have to worry too much about adhering to standards or interoperating with other networks because, I don't know, you're running a data center or you're doing something local to yourself. But the internet remains important, and there are people thinking about new kinds of architectures, new kinds of protocols that could make the internet better, more evolvable, and more secure. And these are challenges that bring on a whole other set of concerns when you're doing things worldwide. So just very briefly, I wanted to thank you all for coming and for, again, POPL''s my home community, so I feel so welcomed to be here. I wanted to thank my mentors who have provided constant support and guidance over the years, and all of my students and collaborators. This is only a subset, but they've really made research really fun. Okay, thank you.
Okay, thank you, Nate, for that wonderful talk. We have a few minutes for questions. There will be a volunteer on this side of the room and on that side, so if you raise your hand, I'll try to get the mic over to you.
Hi, Nate, over there. Yoo-hoo.
It's Peter.
Matthias?
Peter.
Peter Sewell.
Okay.
So this is great. Anything that can tempt the IETF away from rough consensus is an amazing achievement. Most of what you talked about was about expressing in P4 enough for these network components to do their routing or forwarding or filtering jobs. Does the same apply equally to the pretty complex logic you need in the endpoints of higher level protocols, or is that a different game?
Right. So I think the answer, the first answer is no. And I think some people know, Peter had a project, what was it, 15 years ago, net semantics, studying these N-based protocols and all of their complexities as realized by different vendors in this rough consensus and running code world. And there's a whole lot more that goes on, right? There's timers and congestion control loops, and it's much more complicated than what goes on a router. Having said that, I do think that languages like P4 could be one piece of the puzzle. If I had to pick off like one thing that should be a no-brainer for the IETF, it would be, let's not write ASCII art diagrams. Let's have some sort of code description that we can run tests against, and it has a precise semantics. So that wouldn't be the whole protocol, and it might not even be the interesting part of the story from their perspective, but at least then it would lower the bar for doing, for having certain kinds of testing tools at a minimum. If you wanted to prove a theorem, you may still need to do a whole bunch of extra modeling work like your team did. So I don't claim this is the whole story, but I think it could be an important part.
And do you think the IETF could now be brought to appreciate that kind of thing?
Possibly. So there's a group I'm loosely involved with, but a bunch of formal methods people like Ken McMillan and David Basin and others are going to IETF meetings and trying to convince them that they should start to think about formal methods. And the strategy that they've been following is not to sort of say, formalize all the things, because that would be socially probably dumb, but to think about, where are the pieces that are most complicated? So, certain security protocols where, of course, there's already been lots of work by some people in this room on formalizing, security guarantees, or congestion controls, another area where there's a real feeling that sort of, maybe Van Jacobson can keep it in his head, but most humans can't keep the details of these congestion control schemes and whether they're fair and whether they converge rapidly to the, to the right values. So there, some tool support could be helpful. And I think that's the right way to go. Find these kind of problems where there's a real need and where the protocol designers are finding that they're either scared or, unable to deal with the complexities, and think about how formal methods can help, and then maybe build from there.
Absolutely. Thanks.
Hi, Nate. This was a great talk. Thanks. One thing I wanted to ask is, actually, you mentioned a little on your future work about the quantitative aspects, because I've talked to networking people much less than you, but like, performance is one of their highest aims. And I thought, recently there's been a lot of work on sort of quantitative by simulations and things like that. And I wondered if you had, thought about trying to figure out the performance as well as part of the semantics.
So I myself have not worked so much on these things. I had a very brave postdoc, Mina, who's on the slide right there, who had one of these fancy fellowships and decided to work on performance verification herself. So she teamed up with some folks at MIT and Georgia Tech and started to use not quantitative bisimulations, but just using sat solvers, a tool that could model the sort of adversarial inputs that would break some properties of a congestion control scheme. So that's the sort of early work I was referring to. I do think that, of course, there's been a ton of work in our community and formal methods on things like, quantitative reasoning in many forms, and trying to apply that to some problems, I think, would lend some new insights. There would be, of course, lots of challenges to make these things scale and to find the right modeling tricks, what to abstract and what to leave in. But I think that's a very fruitful place to look.
Thanks very much for the excellent talk. With these requests for comment, when people come up with them initially, do they have a well-formed enough idea to be getting formal, or is the looseness of prose kind of useful so that the idea can be bashed about and commented back and forth before maybe investing time in really meticulously working out the detail?
It varies, and I should say I'm not a regular member of the IETF, and I should also just disclaim that I don't bash the IETF. I think what they've accomplished over many decades is truly amazing. So I come humbly as someone who thinks that some of the ideas from our community might be useful, not as someone to saying you're doing your job wrong. I think nowadays, well, let me back up. In the early days of the internet, obviously the IETF was central, and lots of these discussions were developing the design as these things were written. I've only heard stories of some recent protocols like Quick, for example, and some of the congestion control schemes and how those got pushed through the IETF. And often nowadays, at least one model is a company may have, or a group of folks may have already sort of fleshed out a design, and then for various reasons they want to get the IETF stamp of approval. Whether that's to get a vendor to build it, or whether it's to get a raise at their job, or just to sort of build a community around that protocol. So often the serious protocols, I think, often had a lot of work that go into them by the time they get brought to the standards process. There are other, if you read RFCs, they really run the gamut. There are some that are sort of editorials, and there are some that are proposals for specific protocols. But by and large, I think things are reasonably mature by the time they come to the committees.
Thank you.
Okay, let's thank Nate once again.